All right, so I'll get started. Today's Rubin Science Assembly is going to focus on a variety of cutout services that are available in the Rubin Science platform for making image cutouts. And I'm first going to start with a few announcements before getting started with the cutout services tutorials. So I'm going to review a number of tutorials, but I'm also going to have a few slides of introductory material just to get people oriented to the process that is used to make the cutouts. All right, so first, a few announcements. It's some a fun announcement that our the Rubin Observatory founding director Tony Tyson was included in the 2026 Time 100. So this is a list of 100 influential people that was published by Time Magazine. So that's a fun announcement. And I also want to remind everybody that alerts are now flowing as of February. And so you can learn more about the alerts at these web links that I've posted here, including rubinobservatory.org for scientists, where you can find more information about also the brokers that can help you sift through the alert streams. And we have some documentation about the prompt products that are produced at promptproducts.lsst.io, so you can better understand the data products that are produced for that. All right, so a few other announcements. We have the Rubin Data Academy coming up the week of June 22nd. So this is a fully virtual sort of boot camp crash course in using Rubin data and the Rubin Science platform. And so you can register for that and get sort of a nice focused week-long immersion in the Rubin Science platform and the data products that are produced by the pipelines. We also have the Rubin Community Workshop coming up the last week of July. So you can still register until June 22nd or until the capacity has been reached. So there's a limit of 250 registration registered sorry registered participants. So you can find more information about this meeting. It's being held at Slack in Menlo Park, California, and you can find out more information at this web link for the Rubin Community Workshop. And then we also have some upcoming Rubin Science assemblies. So this week we're talking about the cutout service. Next week is a drop-in office hours. Every other week we have drop-in office hours. You can come and get very your specific questions answered. We have staff on hand attending the office hours to answer questions. And then the week after, on June 11th, we're going to have a tutorial about the extendedness parameters in the catalogs. Okay, we also have some other workshops coming up that might be of interest to people. So there's a KaiPack workshop about what Rubin should do after the LSST 10-year survey is completed. So that's the first week of August. It's also at Slack, so you can find out more information. It has a June 1st registration deadline, so that's coming up pretty quick, but there's a web link here so you can find out more information. There's also LSST at Europe happening in September in Hungary, and then LSST at Latam in South America, happening in Brazil. And there's some web links here in case you want more information about those meetings. So I also want to remind everybody that Rubin has a users committee, and the users committee is charged with soliciting feedback from the community about the data products and the science platform. So they want to hear from you about your experiences working with the Rubin data. And twice yearly, they make recommendations to the Rubin Operations Director. And so this is a useful way to communicate your feedback to the project. So there's some links here so that you can find out more about what the users committee is doing and how to contact them. We also want to remind you that the Links Frameworks has office hours, and the Link Frameworks' mission is to enable scientists by developing scalable and productionized software and algorithms in collaboration with the broader community. So you can find out they meet most Thursdays at 10 a.m. Pacific time. So you can see their calendar. There's a Zoom link here, and you can scan this QR code for their website. So there's a number of projects that are ongoing that might be of interest to this group of people. Please look into this if this is something that you're interested to get help with or learn more about what they're doing. All right. Are there any questions about the announcements I just made? Otherwise, I'll move on to the Rubin cutout service. It looks like yeah, you can also ask questions after the tutorials if you want. Um, all right, so I'll just move on to the Rubin cutout services and the notebook tutorials that I'm going to present. So cutouts are a very important functionality because Rubin images are very large. And so visual inspection and for other reasons, it's very useful to be able to make lots of cutouts and visually inspect or see images of individual objects within the Rubin data. And so that's what the cutout service exists for. This a science assembly is going to overview. I'm going to try to overview three tutorials in my 50 minutes, and so I won't show all of the tutorials, but I'm going to show key parts of three different tutorials. So we have two tutorials that are focused on the Rubin cutout service specifically. So this is a notebook 103.4 from our tutorial notebooks repository, if you're familiar with that. 103.4 is focused on making cutout exposures. And so you can see this is a link to the rendered HTML of that notebook in case you don't want to follow along in the Rubin Science platform, but you can also access this notebook from the Rubin Science platform in the tutorials menu. After that, I'm going to talk about image stamps. So this is tutorial 103.9. So the main differences between these two, they both use the Rubin cutout service, but they return the data in a different format. So that they have different science applications, and I'll talk a little bit about that. And then hopefully I have time also at the end to talk about making image subsets with the butler. So this is a specific functionality of the butler that has sort of different science applications, but you can use the butler to make subsets of a full Rubin image if you're sort of working with one Rubin image specifically. And so you can find these notebooks available on our GitHub page, tutorial-notebooks repository. And it's also already uploaded in your RSP account under the tutorials menu. Okay, so I'm just gonna do now a quick introduction to the Rubin cutout service because it has it's you have to sort of just to give you an overview of what the sort of workflow is and what you're doing when you call the Rubin cutout service and what's happening on the back end so you can understand the process. So so this quick conceptual introduction to the Rubin cutout service. Rubin adopts, so Rubin is using a cutout service that is designed sort of to follow International Virtual Observatory Alliance standards. So the International Virtual Observatory Alliance is an organization that decides technical standards for building the virtual observatory, which is this vision that astronomical data sets should work seamlessly as a whole. So Rubin Observatory and the pipeline sort of adopt this VO first approach. So you might be familiar with the Table Access Protocol or TAP service, for example, which is also another virtual observatory standard. So the cutout service is similar in that it's a tool that performs data processing and operations on the remote server. So this is a server-side operations for data access. It's called SODA for short, and it's a web service that you send a command to the remote server, and the remote server will do the processing for you and return the result. So in this case, the SODA is the web service that you're asking the remote server to do is to make the cutout remotely and send you only the small cutout rather than the full image of which is very large. So you can find out more details at this archive posting if you're interested. But sort of overall, the idea is that there are web links that point to remote images on the Rubin server, and we have to find out what that web link is, and we're going to use that web link to specify on the remote server which image we're going to make a cutout from. So just a little schematic that helps to visualize how this happens. So on the Rubin Science platform, you find an object of interest. So you have an RA and DEC for that object. Then you perform a tap query to a catalog called the ivoa.obscore. that identifies what images are overlapping the RA index that you've asked for. And you can also specify the type of image. So, for example, the deep coat image or the exposure, the individual exposure. And then you get that URL from this query, and that URL is now pointing to an LSST image product that is unique on the remote server. So this is basically a data link that sort of uniquely identifies the image on the remote server. So we need that in order to tell the server which image to make a cutout from. So you provide this data link to the Rubin Cutout service. So this is the SOTA service I was talking about before. So we're going to import something called the PyVO package, which is sort of it's a Python package that contains this service that's needed in order to send information to the Rubin Science platform through the Rubin Science platform, sorry, to the database. And then we define this cutout region. So you're going to say we want this centered at this RA and DEC, and we want this cutout to be approximately this size. And then the remote server will make that cutout for you and return it back. And so you receive those bits into bytes into memory, and then you can save it or visualize it or do whatever you want with it in the Rubin Science platform. Does anyone have any questions about this process? I'm going to show you how this works in practice in the notebook tutorial. So this is just sort of just to give you an overview of what's happening on the back end when you make these commands. Okay, if not, then I'll keep going. So I'm going to present a few notebooks that sort of demonstrate different ways that data gets returned to you. So there's currently in the Rubin Science platform, there are three types of cutouts that you can generate. So one of them will return a cutout in the exposure F format. So if you've already been working with Rubin images, you'll know that exposure F is sort of the native image format for Rubin images. So it has the science extension, but it also has a number of other extensions in it, including the variance, the mask, and a variety of metadata, including PSF information and things like that. So it's a big, it's bigger than just a simple FITS file. And this is sort of the standard thing that if you want to use Rubin Science Platform, or sorry, Rubin pipelines to analyze, then you probably want exposure F. You also could receive the image in a masked image F, which is a little bit slimmed down, so it doesn't have all of the extensions of the exposure F type, but it does have the mask extension and the variance images, and this is often what people are most interested in getting. And then you can use these methods to extract the Rubin the science image from these Rubin formats like cutout.image or cutout.variance to extract the different arrays from these image types. So this is the thing I'm going to show in the first notebook, which is called cutout exposures. There's also a third type that returns what's called an image F format, and this is kind of a structure similar to a FITS file. So this is something that you could use with sort of standard AstroPy tools. So there's a extension 0, which contains sort of the primary header and metadata, and then there's extension 1, which contains the image array, basically the pixel data, the science pixel data, and then also an image header that helps you work with that in similar to a FITS file. And this is the thing I'll show in the second notebook. And so just to give you an overview just to give you an idea of what science applications would be used for these, the exposure F and the masked image F you would probably want if you want to use a small number of cutouts that you are going to analyze using Rubin LSST pipeline tools. And image F is a little bit less data intensive, and so you would probably use this if you want to generate more images and work with AstroPy tools to analyze those. And with that, I will go to the Rubin Science platform and sort of get ready to demonstrate these. And so if anyone has any questions about what I just presented in the slides, now is a good time to ask.
Yeah, I
If
had
not,
quick question. Do these
yeah.
return co-added images or single exposures, or is that a setting or an option?
Yes, so you can specify when you identify so when you do the query for what images overlap your array and deck, you specify which type of image you want. So you can do it with a co-added image or you can do it with the exposures.
Okay, thank you.
Um, yes. All right, so if you're following along, I'm going to go to the Rubin Science platform and then I'm going to click on this tutorials menu. And I'm going to go to DP1 because this notebook is going to use DP1 data. And these notebooks are all in the 100 level how to use RSP tools menu. So the first one I'm going to show is under 103 image access and display, and it's called cutout exposures. So we're going to open that notebook, and I want to use the latest version of this notebook. So I'm going to click overwrite because I had this open earlier. Um, all right, and so here is the notebook. So I'm going to quickly go. I'm going to try to cover part of this in about 15 minutes. So I'm not going to show the whole notebook, but I'm going to give you an overview for how this works. Okay, so this notebook, again, like I said, is using these IVOA tools to generate these image cutouts using the Rubin Science the Rubin Cutout service. So an important package that we're going to import here is this PyVO package, and the PyVO package is going to give us access to these tools that, like the SOTA query, that allows us to send the commands to the remote server to do the operations on the remote server. Another thing I want to point out here is that we need to import this RSP utility called get PyVO auth. So because the Rubin data is proprietary, you have to send an authorization to the remote server to let it know that you're authorized to make these cutouts. So we're just going to import that so that we can tell it the remote server that we're authorized to use it. All right, so we're going to import these packages. There's a number of other things you may recognize here. We're also going to set the backend for image display as matplotlib. And first, we're going to initiate the SIA service. And so SIA is another IVOA standard that allows you to query image data from archives. So this is one way that you can figure out which image is overlapping your location on the sky of interest. So we're going to initiate the SIA service. And in this case, we're going to we're going to make a cutout of a visit image. So this is one of the individual exposures and not the deep coad. But they both work similarly. You just specify which type of image you want. So in this case, because the visit image, each part of the sky gets mapped by many different visit images, we need to specify some parameters to identify the image that we want. So in this case, we're going to specify the RA and DEC, and we're also going to specify the time that the image was generated. So you specify this in MJD, and you need to specify also which band you want. So we've specified here the R band, and we're doing that through this effective wavelength parameter here. So I'm going to do this, and then we're going to query the SIA service for visit images that meet these criteria, meaning that they were taken over this part of the sky at this particular time. So here we're going to define the center that we want to search around. And then we're going to ask for a, we're going to ask for the images that overlap this location with this time frame that we defined also. So here we found one image that overlaps that we found one visit image that overlaps this part of the sky during a very narrow range of time frame that we specified. So here is where you can specify which type of image you want. So here we've specified a visit image. So then you can write this to a table so you can see what comes back from this query. So we've retrieved a data product subtype that is a visit image. So that's what we want. I want to just go over here to an important thing called the access URL. So this is this return here is specifying the remote location of this visit image that we queried for. So this is the thing that we need to send the SOTA service in order to generate the cutout. So then you can also see the location of the time when the image was taken and a bunch of other things about the metadata about the image. But this access URL is the key thing that we're going to need. So this contains the web URL for the image. You can also do this with the tap query if you're more familiar with that. So there's an obscore table, a table called the obscore table that contains the metadata of these images. So we've just put an example tap query if you prefer to use a tap query instead of a SIA query. Okay, so now I'm going to generate an image cutout. So the first thing we did was we pulled out this access URL. Um, so then we have to put this in the right format. So we're gonna, so results is the table we got back from our SIA query. So we're gonna extract the access URL from that and store it in this thing called data link URL. And then we're gonna feed that to the data link results, which was something that we imported from the I think it was PyVio. Sorry, now I forgot where it was. Yeah, so we imported this from the PyVio package, which is the virtual observatory package for telling the remote server the operations we want it to do. So we're going to send this data link there, and we also are going to authorize ourselves to get through this get PyVio authorization. So this happens automatically because if you have a Rubin Science Platform account, you already are authorized. And then we store the data link here. Um, so that and here you can print it out. So we retrieved the data link. The data link checked that the source is there, and it gives us the URL to this image. So now we're going to call the Rubin image cutout service. So we also imported this thing called soda query, which is the commands you send to the remote server to do the cutout. And we have to tell the remote server what service. There's a number of different services that you can have the remote server do, but we want it to make a cutout. So we're going to give it this command cutout dash sync dot dash exposure. So cutout, so these three, I told you in the slides earlier that there are three different ways you can retrieve image formats back from this cutout service. So this one is going to call the exposure F type. So that's what the dash exposure at the end of this is. And then we're going to store this here in SQ. Okay, so that is now holding the result of this SOTA query. Um, we need to now tell the SOTA query what kind of cutout we want it to make. So here I'm going to define the RA and dec of the target as the center location of this cutout. And then I'm going to define a radius. This is a little confusing because there's a few ways you can make a cutout and define the shape, but the sort of fastest way is to use a circle. It doesn't return a circle, it returns a square, where the square is defined by the diameter of this circle, basically. So we're going to define the radius of the circle as half of the edge. So we're going to tell it to be 0.01 degrees. Then you can send these parameters here with this method called circle, and it will generate the cutout remotely. Then we need to retrieve the cutout, the sort of bytes that make up the image cutout on the RSP, and we're going to do that here with this execute stream command. So now on your account of the RSP, you're going to have this cutout bytes in memory that you can then read out and use for analysis. So we're going to do that in this cell where we're going to use this thing called mem file manager. So this is a package that will hold the memory and you can tell it what you want to do with those bytes that are currently in memory. So we're going to define the memory container to hold these bytes from the cutout. We're going to tell it with this set data thing that we want to have it be an image cutout of this shape, and then we're going to ask it to read it in as an exposure F format here. Okay, that's a lot, so I'm going to pause and see if anyone has any questions about that procedure. Okay, I think so. Another thing to note is that I think in the future, these things are still under development by the data management team, and so I think in the future we can probably expect there to be a package or sorry, a function, a built-in function that will do some of these things um, do these things automatically if you just call a function, but that's not developed yet. So All right. So now we want to display the image cutout that we just generated. So we're going to define display for us to plot, and then we're going to give this display this exposure.image. So exposure is holding the exposure F cutout format, but we're going to ask it to just display the sort of science pixels here by attaching dot image to the end. Okay, so this is the image cutout that we made from the on the remote server. Okay, so does anyone have any questions about that? That was about 15 minutes. So the rest of this notebook, I'll just point out, has a number of other things of interest, like extracting the WCS information. If you want to save these cutouts as a FITS file or save it on disk, we have some example code of how to do that. There's also, I mentioned that we used this circle to define the cutout, but you might want a non-square cutout, and so you can use polygon instead to define like a rectangular cutout. So we demonstrate how to do that here. And then I also demonstrate at the bottom how to extract the other format, meaning the masked image F format here. So it's exactly the same procedure, but you're just sending the SOTA service a different service name. So you're gonna, instead of doing cutout sync dash exposure, you're gonna do cutout dash sync dash masked image. And this gives you sort of the slimmed down version that doesn't have all of the metadata, but does have the image, the variance, and the mask for the image. And that sort of works the same way. Okay, so that's it for this first notebook. This is the notebook where if you want to use LSST pipeline tools to analyze the images, the return of these cutouts are going to be in the right format for that, and it will allow you to use the WCS tools and other things that are sort of built into the uh, LSST pipelines. But this does transfer more data because these image types are larger, and so this is less optimal if you're going to do many cutouts. Okay. Well,
Yeah,
everyone should feel
excuse me.
free. Oh,
Uh,
yeah. Go ahead.
yeah, so I had a question, and your last point was just a good segue, which is on average, how long does it take to get a cutout? And if we want to do this at scale with many bands, what's the best approach?
Yeah, so right now these are a little bit slow. So this particular example, I mean, I think you saw it varies a little bit depending on like what's happening, you know, how many other people are using the Rubin Science platform at the same time. But these, you know, you saw it took a couple seconds to get that image to come over and to do that cutout. So it doesn't scale up very fast. The notebook I'm going to show next is for bulk cutouts, which still it's producing a smaller data product, so it does operate a little bit faster, but in my experience, it hasn't really been super noticeable what the difference is. And so I should mention that these tools are still under active development, and I think the data management team is aware that scaling up to generate like thousands and thousands of cutouts is something that people want to use. And so they're working on that for probably the way that would work is that you send the query to the remote server to do all of these cutouts in bulk. And that's going to be something that we can expect for data release one, but probably won't be ready for data preview two.
Okay, thank you.
Does that answer the question or?
Yep,
Okay.
yeah, it does. Thanks.
All right, cool. Okay, I'm going to close this and open the next tutorial. So the next tutorial is still under the DP1 menu and under 100, how to use RSP tools, and under 103 here, and it's called image stamps. Okay, so this is going to work exactly the same way as the last notebook. So I'm going to go through it a little bit faster. The science application for using this third type of uh, cutout tool is to return an image F format, which is a little bit slimmed down, so it's less data transfer. But as a result, you can't necessarily use the RSP or sorry, the LSST pipeline tools because the image format is now different than what the Rubin image format is in its native form. So you would want to use AstroPy or other tools to analyze images this way. But it is smaller, and so you will take less time to generate and transfer the cutouts. All right, so this is all similar material to the last notebook. So I'm just going to import this here. These imports are larger because it demonstrates how to work with these image F formats. And so there's more AstroPy uh, tools that are needed in order to import and access to manipulate these images. One thing that is different that I'm going to point out. So here you see some similar things from last time. So we have the get PyVO auth for the authorization. You see the memory and the memory file manager and display tools. Here we're importing the image F type from the image package of LSST. But image F is basically sort of what you expect from just a typical FITS file that you might see in other contexts. And so, of course, we're also going to import the same PyVO packages that allow us to send these commands to the remote server. One thing I want to point out here is that we have to import this reproject package. So reproject is an AstroPy adjacent package that allows you to work with WCS rotating images to match different WCS um, so that you can sort of match different images with different WCS. And so this has to be imported because now we no longer have access to the WCS packages that are native to the LSSD pipelines. We have to sort of use external packages to work with that. All right, so I'm going to import this. And again, like last time, we're going to define some of these parameters and functions. So we're going to initiate the tap service and initiate the SIA service. And we're going to set the AFW display to be matplotlib again. Okay, so in this case, we're also going to save some of these image stamps as FITS files. So this just sets up a temporary directory on sort of what's considered the scratch directory, which is called deleted Sundays. And you have your own subdirectory in there with your RSP username account, but it's going to be deleted once a week. So that's just something to be aware of. Okay, so we're within your sort of Scratch directory. So here it's found that my username has a Scratch directory already. Within that, to sort of keep things organized, we're going to just define this other temporary directory called DP1103-9 temp. This is just named after the notebook, so you can keep track of where these images go. So I'm going to do that, and then I just clean things up by deleting some of these variables we're not going to use again. Okay, so in this case, since one of the applications of this is to make lots of cutouts and then sort of visualize things, for example, a transient changing over time, uh, it's kind of nice to visualize this by making a GIF out of those images. So I just have this quick function that we're going to define that allows you to retrieve all of those FITS files that you save in that temporary directory to make a GIF out of them. Okay, so then, like I mentioned before, the RSP team is probably going to, at some point, make an automated function that you can call to do all of these steps. But in the meantime, because we're going to be doing many of these image cutouts, I'm just going to quickly define something here myself, which is called get cutout, which it does all of these operations, including calling the SOTA query, um, after you send it the data link, which you've retrieved from the query, and then also the RA and DEC. And field of view here is the size of the cutout that you want it to generate. So here I'll note in the past notebook, we were looking at cutout-sync-exposure and cutout-sync-masked image as the service that would generate image cutouts of those formats. In this case, this slimmed down version is called cutout-sync. So we're changing the service we're calling, and that's really the only difference here compared to what we did before. So I'm going to compile this function. I also am going to make lots of cutouts because the application of this is to make lots of cutouts. And so I'm going to just generate some plotting conventions to make the grid of cutouts easier to visualize. So I'm just doing that. It's just setting up so that you plot many images in a sort of organized way. Okay, so the first thing we're going to do is find a transient. So I'm reusing a Type 1a supernova that was discovered in DP1 imaging um, from a different notebook. Its location is already known from that notebook, so that's this RA index. So I'm going to just define that. And we're going to retrieve three stamps for this transient. We're going to get the science image, the template, which is made from many. So the science image is the individual visit that in which the transient was discovered. Then we have the template image, which is a stack of many images from before. So we compare this new visit to the template, so we see what it normally looks like when there isn't a supernova going off in it. And then we're going to also generate a cutout of the difference image so you can see what changed. So here we're going to define again the RA and DEC and the that we want to generate a cutout of. And then we're going to perform a query to find the images that span a time when this transient was changing and is detectable as a DIA source. Um, DIA stands for difference image analysis. So we're going to define this query. We want to find out the time when it was first detected, the idea of this DIA object, which is a unique identifier, and then we have the RA and DEC and the search radius here. So we're going to run this query and store the table as DIA results. And so we have these key things that we need: the first detection, the last detection, and the object ID here. And then we're going to query the CS service for images that overlap this thing during that time frame. Okay. And then we want to find R-band images and only return the one where there was the first detection of change. So that's what this cell is going to do. Um, oh, actually, sorry, we're not picking, we're going to find all of the images when there was a change. So there's 114 visits that were taken during this time frame when there were changes happening. So now we're going to use the SIA service to find the template coad image and the difference image that overlap this area. So we're going to do that here. Sorry, I'm going kind of fast because I also want to get to the Butler subsets version, which uses a different application to generate cutouts. But please feel free to ask me questions about this if you're interested. Okay, so now we're just storing some information about the range over which this DIA source was changing. Okay, so now we're going to get data links for these three different kinds of images. We want to get the science image, we want the reference image, and we want the difference image. So we're going to store these as different data links because all of these images are stored on the remote server. We want to get cutouts of all of them, so we need unique URLs for each of them in order to send it to the cutout service. All right, and then we're going to retrieve the stamps using the same methods we did before, but we're gonna just to wrap everything up in this function that makes it faster, we're gonna make use of the get cutout function that I defined at the top of the notebook. That sort of speeds the amount of code, it decreases the amount of code you have to call in a specific cell. So we're gonna give it a cutout size of 0.004 degrees, and we're gonna generate this cutout for the science image at this RA and DEC. We're gonna send the authorization and send it the cutout size. Okay, so this is gonna take a minute because we're generating three different cutouts instead of one. So this took about 6 seconds to do three images, and then we're gonna display them. All right, so this is the science image from the visit that was taken. This is the template, and this is the difference. And so you see here that the visit images are always at sort of varying angles, and the template images are always aligned to the sort of grid of co-added images. So if you've been to other of our science assemblies, you'll probably have learned that the whole sky is split up into this grid of patches and tracts that is a that we rotate all of the visit images onto that grid so that they can all be stacked and co-added with the same WCS. And so the individual visit images are not already rotated; they're at a different angle. But these difference images are measured are generated after this rotation. So here you see the difference in rotation between here. So we need to change that. And the way that we're going to do that is using we're going to have to extract the WCS from the header of this image F format. So in the past notebook, we were using LSST pipeline tools to do things like that. In this notebook, we can't because we asked for a very slimmed down image F type. So we can't use LSST pipeline. So we're just going to extract the WCS from the header, and we're going to use this AstroPy function called WCS to sort of store the WCS information that we need. So we're going to do that for the primary science image and also for the reference image so that we can rotate the science image onto the reference image coordinates. Okay, so I've extracted that, and then I mentioned earlier that we're going to use this reproject package, and we're going to use it here to rotate the science image onto the same WCS as the reference image. And now we're going to plot the rotated one. And so now you see that this reprojected visit image, the science image that we extracted before, is now aligned with the template image. So this gives you a demonstration of how to manipulate the images so that without the LSST pipelines. All right, so the rest of this notebook also shows sort of how to do this for bulk image stamps. So like you mentioned earlier, if you want to make lots of images to visualize changes, for example, then this is the tool that you would use. So this section 3 is just, I'm going to go through this very quickly so I have time to do the other one. This is just going to generate a range of visits for this transient. So we're going to do 20, and it's going to generate these science cutouts for this transient over time. So you get a number of different cutouts. And so you can see it's not like instantaneous. I mean, this is going to take probably a minute or two to generate all of them, depending on what else is happening right now. So we're just going to give this a second. I can pause here while this is generating to see if there's any other questions about this particular notebook. Otherwise, we can wait for this to finish computing. There we go. Okay. All right. So I've now just plotted one of them as an example here. We also saved these images in our temp directory. So this instead of storing it in memory, we've written it out into that temporary directory in the Scratch. And so here we're going to read them in and plot them. So we stored them as ping files, which is a little bit different than the FITS files, but this does allow us to make sort of work with these GIF and visualization things a little easier. So here is a grid of all of the exposure, or sorry, all of the visit image cutouts that we generated. They've all been now rotated to match the template image. And so you can see kind of how this transient is changing. It's hard to see because the transient is inside a host galaxy, so you see mostly the host galaxy. So we're going to show in a second how to visualize with an animation here. Okay, so here you can see this is now taken those 20 exposure cutouts, visit cutouts, and turned them into a GIF is in chronological order. And so mostly you see the PSF and other things changing in this image, but this is at least a demonstration of how you would go about generating lots of cutouts for transient, for example. All right, so that's the end of this notebook. We have about 10 minutes for me to show the last notebook. So if there's no other questions on the Rubin cutout service, I'll show how to generate image subsets from using the butler instead. So please feel free to ask questions while I load up this new notebook. So that's also in the 100 level directory. Now, instead of 103 image access, we're going to go to butler data access. And the notebook is 104.5 image subsets with the butler. Okay. So all of those demonstrations I just showed are good for science applications where the cutouts you need are not all from the same parent image, meaning that you are going to be wanting cutouts from many different visit images or many different deep coads on different parts of the sky. And that's not always what people want to do, and that's not always going to be the fastest thing. Some science applications require that you make small cutouts from a single Rubin image, like for example, a single visit or a single deep coad patch and tract. So things that are near each other, for example, or something like that. And so in that case, it can be useful to instead use the butler to generate image, what we're calling image subsets. So these are still cutouts, but they're cutouts from a specific single image, and the butler can be effective for doing that. All right, so in order to do this, so the way you define cutouts to send to the butler is by using bounding boxes. So this notebook demonstrates a lot of applications related to how to define bounding boxes and how to feed those bounding boxes to the butler after you've retrieved an image or after you've identified on the remote server a single image with the butler that you're wanting to work with. So here, in this case, we're importing a bunch of functionality related to these bounding boxes here. So these are just sort of spatial definitions that you can use. We also are defining the butler here, which is an LSST pipeline functionality that sort of serves images to you on the Rubin Science platform. And then we also have here, again, we're going to define the exposure. We're going to import the exposure F package because these images from the butler will all be in exposure F format. And local and parent are just some other functionality that allows you to change how you define the coordinate system of these bounding boxes. So I'm going to import these. And then we're going to instantiate the butler. So the butler, we're going to tell the butler that we want to work with DP1 data, and we're going to use the collection called LSST ComCam/DP1. Um, and then again, like the other ones, we're going to set the AFW display backend to be matplotlib. All right, so now we're going to do the same thing we did before, which is define a center that we want to work with on the sky, and then we're going to define uh, a region where we're going to search for images that overlap here. So this RA index is in the extended Chandra Deep Field South data, so we're going to work with deep coad data now. So the first thing that we're going to do is identify the deep coads that overlap this region. And so you do that using the butler with this query datasets function. So we're going to ask for deep coad. We're going to ask for the band to be the R band. We want it to overlap the RA and DEC. And we're going to order the return by patch and tract. Okay, so and here we're just going to get the data ID that is, there's going to be lots of images that overlap our RA and DEC potentially, so we're just going to take the first one. So we're going to store the image we retrieved as coad. And now you can define regions within this coad using the bounding box. So the first thing we're going to show is what the bounding box of the parent image is. So this is an entire patch and tract, so it's quite big. So we're going to just ask it to tell us what are the bounding boxes, the bounding box definition for this image. And so you'll notice it's not going from 0 to the maximum pixel size. It is going from 8800 to 12200. And so this is because this image is the coordinates here are for the entire tract, and we've just asked for a patch of it. So the patch starts at tract coordinate corresponding to these pixel values. So this is what we call the parent um, coordinate system. You can also ask for local, and local is in the coordinate system of the patch itself. And so here it's starting at pixel 0 because it's the local coordinates, and then it goes the size of the patch is 3400 by 3400. So that's why you have this local range here. Okay, you can also ask for there's various bounding box methods that you can use to access useful information about it. Like for example, what is the maximum pixel coordinate? Um, and what are the dimensions of the coad? Okay, so to define a subset, we need to define a bounding box for a smaller cutout. So we're going to use this function called box2i to define the subset. So this is stands for 2D integer bounding box. So we can just pick something. Here we're going to pick a smaller subset that's about 1,000 pixels on a side. And so we're going to use the get dimensions to find out what the total is. We're going to find the center of the image by dividing by 2 here. So this is the subset center is going to be right in the middle of this coad. And then we're going to ask for the subset to be 500 pixels on a side. And then we're going to define this bounding box using this box2i. We're going to feed box2i these different coordinates that we want to define the shape of the subset that we're going to make. And then you can define the bounding box for this subset. So that's what we've done here, subset underscore box. You can also, we demonstrate a few different ways to do this. So this is maybe a more compact way to do that using also the point 2i and the subset or the extent 2i. And I don't really have a lot of time, so maybe I'm just going to skip through this and just point to the fact that you can define bounding boxes using a variety of useful tools here. Okay, so that was defining bounding boxes using pixels, but that's not always what people want to do. Sometimes you want to define the bounding box according to on sky coordinates. And so we also demonstrate how to use the sky coordinates to define the bounding box for this image subset. All right, so now the butler has already identified this deep coad. We want to pass the bounding box to the butler in this parameters um, dictionary. So we have this subset bounding box defined using the sky coordinates here. And so what we're going to do is pass these parameters directly to the butler here. So we're going to ask the butler to send this deep coad using the data ID that we had retrieved earlier. And we're going to feed these parameters saying that we want to just retrieve the subset using this bounding box. And then we're going to store this in subset image, and then this will store the science pixels in this image array. So we're going to do that. Okay, so we've created a subset of shape 300 by 300 pixels. So that was corresponding here to having 60 arc seconds on a side. And we are going to now plot that. And so here's the image subset that was retrieved by the butler. So this is useful if you're wanting to make lots of these little subsets from the same parent image. And that would be the science application for this. So this notebook goes on to do demonstrate some other ways of retrieving these subsets and how to retrieve multiple subsets here. I'm going to skip over all of this and just see if there's any questions because we only have a few minutes left and I want to make sure that there's time for questions. But this is just to sort of get you oriented and point you to some resources where you can now find out more information on how to make these image cutouts using different functionalities. All right, so that's it. I'm happy to take some questions in my last few minutes here.
Did you mention, Christina, if this will be available, the recording, or how we can access it?
Yes, so I'm recording it and we're going to post the link to the recording. It's going to get posted on YouTube and we're going to link it to the original post on the community forum so that you can find it.
Let's see. All right, thanks a lot.
Sure.
Maybe could you show how to create this 27 AGN steps for fun?
Sorry, can you ask again the
Oh,
question?
maybe you can just showing how to do this, creating 27 AGN stems example.
Just run this. Okay, yeah. Right. So the rest of this notebook, so let me just run the rest of it. I think maybe I only need to run this last part. So in this last little demonstration at the at the end here in section 4, I picked a bunch of AGN from that are known already from a different study. So storing them as a list of targets, then you can send that list of targets. This is just setting up the plotting to make it look nice. But here, then for in the targets, I'm just generating lots of cutouts, and so you can see this grid of 27 AGN from the literature that are in the ECDFS field. So since they're all in the ECDFS field, they're all sort of near each other. So it's uh, actually I think some of them might be in different patches and tracts though. I think I deal with that here though, so it's fine. Yeah, so we find the patch and tract for the AGN and then store a new data ID when I'm plotting these. So anyway, this shows you kind of um, how to generate many of them. It's a little bit slow because this isn't the ideal. Um, there we go. So here now shows the cutouts for each of the AGN from the literature that I was making subsets for. Abi.
Yeah, I had a question not related so much to the cutouts, but it came up as a question while you were describing stuff. The tracks and patches, do all patches in the same tract share the same tangent point? Or does each patch have its own tangent, use its own tangent point?
Mm,
In other
does
words,
anyone-
is the pixel scale the same for all patches in the tract?
Yeah, that's a good question. Does anyone know the answer to that?
And I said it's the wrong place to ask, but since nobody was asking, I thought I'd float that.
Um, yeah, I don't know. We can find out the answer for you though.
Thanks.
Um, all right. Well, if there's no other questions, maybe it's the end of the hour, so but definitely feel free to ask further questions as you explore the cutout services.
Thanks again.